Welcome to This Explainer. We really like to think of our digital security as this realm of perfect abstract mathematics, right? We tend to picture encryption as an impenetrable fortress where these flawless algorithms just stand guard, endlessly calculating prime numbers to keep our data completely safe. But there is this, well, paranoid underlying truth that security experts whisper about. A massive flaw not in the math itself, but in the physical reality of the world we inhabit. Today, we're exploring a pretty terrifying illusion, the illusion of perfect mathematical security. Because while your encryption might be totally unbreakable in a vacuum, your computer, and actually your own body, are physically, constantly bleeding secrets right out into the environment. Okay, let's dive right into this intense reality. Just look at this quote. They lied. It's not listening to your voice, it's inhaling your dead skin cells. I mean, wow. Genomic data is literally the most personal form of data we possess. But while we're out here worrying about smart speakers listening to our conversations, the truth is actually far stranger. We are leaving a permanent, completely invisible trail of our most private keys absolutely everywhere we go. And we're not just talking about the digital footprint you leave online, but the actual physical dust settling on your keyboard right now. So let's get into part one, the physical bypass. Imagine installing a totally unpickable, state-of-the-art lock on a fragile glass door. I mean, why bother picking the lock when you can just smash the glass, right? This is what we call a physical bypass, or what hackers refer to as a side-channel attack. As you can see from the definition here, an attacker doesn't even need to break the complex math of an encryption algorithm. Instead, they just listen to the machine working. See, when a computer processes data, it exists in the physical world. It draws power. It makes noise. It emits heat. A side-channel attack exploits the information that's inadvertently leaked by the system's actual physical implementation. The hackers are quite literally listening to the machine sweating as it works. So how exactly does hardware bleed these secrets? Well, take a look at these bullet points. They're basically the 5 senses of a cyber attack. Timing variations are kind of like measuring a processor's heartbeat. If you observe exactly how long it takes to perform a cryptographic operation, that can reveal the entire secret key. Power monitoring is like listening to the machine breathe, mapping out every tiny fluctuation in electrical current. Acoustic emissions actually allow attackers to hear the high-frequency whispers of a CPU when it's under stress. Heat signatures can be picked up by thermal imaging, and fluctuations in current can even broadcast the machine's secrets over invisible radio waves. It's wild. And get this. This isn't even some new cutting-edge problem. Physical vulnerabilities are practically ancient in the tech world. According to declassified NSA documents, way back in 1943, an engineer at Bell Telephone was looking at an oscilloscope and noticed these decipherable spikes on the screen. Those spikes directly correlated with the decrypted output of a secure encrypting teletype machine. Decades before the modern internet was even a thought, engineers literally saw decryption secrets leaking straight into the physical room. Of course, we do try to fight back. We try to hide these physical leaks using a countermeasure called masking, or sometimes it's called blinding. It's a pretty fascinating 3-step process. First, the system transforms and randomizes the secret data. Second, it performs the actual cryptographic operation on this newly randomized data, which means anyone listening to the power draw or timing only hears garbage noise. Finally, it applies a subsequent transformation to restore the true intended result for the legitimate user. We are constantly trying to jam that physical signal with noise, but it's an endless game of cat and mouse. Which brings us to part 2, biology's leaky hardware. So, just as a computer processor bleeds power and heat, we human beings are constantly bleeding our genetic code. For digital hardware, the side channels are heat, sound, and radiation. But for our biological hardware, the side channels are the microscopic fragments we leave behind literally everywhere we go. Skin cells, hair, and what scientists call environmental DNA, or eDNA for short. We are continuously broadcasting our ultimate source code into the physical world, and it is completely unencrypted. Now, this whole field of study actually started out incredibly innocently. Ecologists basically pioneered eDNA analysis as a cool way to track wildlife. By just scooping up a cup of ocean water or river water, they could extract the genetic signatures floating around in it to see if sea turtles, fish, or specific endangered species had recently swum through that exact area. They didn't even need to see the animal. They just needed to read the genetic dust left behind in the environment. But here is where the story takes a massive, honestly terrifying turn. Forensic scientists realized, wait a minute, this doesn't just work on turtles in the ocean. Last year, a team from the Oslo University Hospital's Forensic Research Center ran a pilot program. They wanted to see if they could recover human DNA directly from the air. And guess what? They did. They successfully constructed full CODIS profiles, which is the exact standard the FBI uses for criminal identification, using absolutely nothing but airborne human DNA pulled out of thin air inside a standard enclosed office space. Think about the privacy implications here. They are deeply concerning. As highlighted here, eDNA can reveal highly sensitive medical conditions and ancestral backgrounds. Just like a side-channel attack pulling a password from a humming CPU, someone with a commercially available sequencer could potentially pull your medical predispositions straight from the air you exhaled in a waiting room. And they could do it entirely without your consent.
All right, let's jump into part 3, hacking the genetic code.
So we have digital systems that are vulnerable to the physical world and biological systems actively leaking our source code. What happens when hackers target the actual machines analyzing our DNA? Nasreen Anjum, a researcher from the University of Portsmouth, warns us about this. She says, protecting genomic data isn't just about encryption. It's about anticipating attacks that don't yet exist. She is raising a massive alarm on a critically neglected field known as cyber biosecurity. To understand how this works, we have to look at next-generation sequencing, or NGS. This is the technology powering modern medicine, diagnostics, and forensics today. The workflow is this incredibly complex chain of both physical and digital steps. First, you have sample preparation, then the physical DNA sequencing, and finally, data analysis and interpretation. Every single one of these steps relies on highly specialized instruments, software, and connected systems. And here's the kicker. Every single link in that chain introduces a brand new vulnerability, a new side channel for an attacker to exploit. The threats her research team identified honestly sound like pure science fiction, but they are rapidly becoming our reality. Because so many DNA datasets are openly accessible online right now, attackers could use AI-driven manipulation to just alter genome data, sabotaging medical research or potentially even framing individuals. They can use re-identification techniques to strip the anonymity right out of supposedly private medical databases. But the most mind-blowing threat of all? Synthetic DNA-encoded malware. Hackers could theoretically encode malicious software directly into a physical strand of synthetic DNA. It would be designed to exploit and crash the sequencer machine the exact moment it tries to read the genetic code. The physical dust itself literally becomes the computer virus. Let that sink in. So, what do? That leads us to part 4, securing the physical world. How on earth do we build defenses for this unprecedented cyber-biological convergence? Well, the paper recommends a frantic race to establish practical solutions right now. We absolutely need secure, hardened sequencing protocols that operate under the assumption that the physical sample itself might be hostile. We need radically advanced encrypted storage for all this biological data. And we definitely need AI-powered anomaly detection that continuously monitors the biological sequencing process for any digital tampering. But honestly, beyond just the tech, securing this frontier requires something incredibly rare: unprecedented interdisciplinary cooperation. We need computer scientists, bioinformaticians, and cybersecurity professionals to stop working in their own silos and start building unified defenses together. Which leaves us with this lingering, almost paranoid realization to end our explainer on today. Just think about the space you are sitting in right now. By the time you finish watching this, the environment around you has already collected enough of your shed cells to build a complete digital genetic clone of you. We focus so incredibly much on mathematically encrypting our hard drives and digital lives, but when every breath, every heartbeat, and every touch leaks your ultimate private key into the physical world, who's really listening? Thank you so much for joining me on this deep dive today, and as always, stay curious.